Module 2, Applied and Advanced Metallurgy. 1. Introduction to Applied Metallurgy. In Module 1, we build the foundation, the science behind metals, their structures, their mechanical properties, and how those properties can be modified. In Module 2, we'll shift to the practical and industrial applications of metallurgy, diving into how metals are extracted, refined, shaped, protected, and applied in real-world engineering contexts. We will also explore modern trends in metallurgy, from nanotechnology to sustainable materials processing. 2. Extractive metallurgy. Extractive metallurgy deals with the processes used to obtain metals from ores and other raw materials. This includes mining, ore dressing, smelting, refining, and alloying. 2.1 Stages of metal extraction. Mining, removing ore from the earth's crust. Crushing and grinding, reducing ore to small particles to liberate metal-containing minerals. Concentration, or dressing, using physical and chemical processes to separate valuable minerals from waste rock, gangue. Reduction/smelting, chemically converting the concentrated ore into metallic form. Refining, purifying the metal to remove residual impurities. 2.2 Major extraction methods. Pyrometallurgy, uses heat to extract metals, e.g., iron from hematite in a blast furnace. Hydrometallurgy, uses aqueous chemistry to extract metals, e.g., gold cyanidation, copper leaching. Electrometallurgy, uses electrical energy for extraction or refining, e.g., aluminum via the Hall-Héroult process. 3. Iron and steel production. Iron and steel are the backbone of modern industry. Their production is a prime example of large-scale metallurgy. 3.1 Blast furnace process for pig iron. Charged materials, iron ore, coke, and limestone are added to the furnace. Chemical reactions, coke burns to produce carbon monoxide, which reduces iron oxide to molten iron. Byproducts, slag, from limestone, and gases, mainly CO2. 3.2 Steelmaking. Steel is produced by reducing the carbon content of pig iron. Basic oxygen process, BOP. Pure oxygen is blown into molten pig iron to oxidize impurities. Electric arc furnace, EF melts scrap steel using electrical energy, often for recycling purposes. Steel is then alloyed and heat-treated to meet specific strength, toughness, and corrosion resistance requirements. 4. Non-ferrous metal production. While iron dominates in tonnage, non-ferrous metals like aluminum, copper, zinc, and titanium are equally important for specialized applications. 4.1 Aluminum. Extracted from bauxite using the Bayer process to produce alumina, Al2O3. Alumina is reduced to aluminum metal via the Hall-Héroult electrolytic process. Lightweight and corrosion-resistant, aluminum is vital in aerospace and packaging. 4.2 Copper. Obtained from sulfide ores using flotation, smelting, and electro-refining. Excellent electrical conductivity makes it indispensable for wiring and electronics. 4.3 Titanium. Produced via the Kroll process using magnesium reduction of titanium tetrachloride. High strength-to-weight ratio makes it ideal for aircraft and biomedical implants. 5. Powder metallurgy. Powder metallurgy is the production of metal components from fine metal powders. Process steps. Powder production, atomization, reduction, electrolysis. Compaction of powders into desired shape under high pressure. Sintering, heating below the melting point to bond particles. Advantages. Minimal waste. Ability to create complex shapes. Tailored microstructures and properties. 6. Metal forming and shaping processes. Once metals are extracted and refined, they must be shaped into usable products. 6.1 Casting. Pouring molten metal into molds to solidify in the desired shape. Sand casting, die casting, investment casting. Suitable for complex shapes and large components. 6.2 Forging. Shaping metal by applying compressive forces. Open die, close die, and press forging. Produces strong, tough components due to grain refinement. 6.3 Rolling. Passing metal between rollers to reduce thickness or produce sheets, plates, and structural sections. 6.4 Extrusion. Forcing metal through a die to produce rods, tubes, and profiles. 6.5 Drawing. Pulling metal through a die to make wires and cables. 7. Welding, joining, and fabrication. Joining metals is essential in construction, manufacturing, and repair. 7.1 Welding. Fuses metals together by heat or pressure. Arc welding, SMAW, MIG, TIG. Resistance welding, spot, SIM. Energy beam welding, laser, electron beam. 7.2 Brazing and soldering. Use of filler metals to join without melting the base metals. 7.3 Mechanical fastening. Bolts, rivets, and clamps, used when disassembly is required. 8. Corrosion and protection of metals. Metals tend to revert to their or form through corrosion, a natural degradation process. 8.1 Types of corrosion. Uniform corrosion, even attack over the surface. Galvanic corrosion, between dissimilar metals. Pitting corrosion, localized holes. Crevice corrosion, in shielded areas. Stress corrosion cracking. 8.2 Prevention methods. Material selection, use corrosion-resistant alloys. Coatings and paints. Cathodic protection, sacrificial anodes, impressed current. Environmental control, reduce humidity, remove corrosive agents. 9. Modern metallurgy and advanced materials. 9.1 Nanostructured metals. Extremely fine grain sizes improve strength and wear resistance. 9.2 Shape memory alloys. Metals like nitinol return to their original shape after deformation when heated. 9.3 High entropy alloys. Alloys with multiple principal elements offering unique property combinations. 9.4 Additive manufacturing, 3D printing, in metals. Layer-by-layer fabrication using metal powders or wires. Allows for complex geometries and rapid prototyping. 10. Metallurgy in sustainability and recycling. Modern metallurgy also focuses on minimizing environmental impact. Recycling scrap metals to reduce mining. Energy-efficient smelting and refining methods. Designing alloys for easier recyclability. 11. Safety in metallurgical operations. Metallurgical processes involve high temperatures, molten metals, toxic fumes, and heavy equipment. Safety protocols include personal protective equipment, PP. Ventilation systems. Proper training in handling molten metal and chemicals. Fire and explosion prevention. 12. Conclusion of Module 2 and course wrap-up. In this module, we've moved from theory to practice. How metals are extracted and refined. How they are shaped, joined, and protected. The innovations shaping the future of metallurgy. Metallurgy is both an ancient art and a modern science, a discipline that connects chemistry, physics, and engineering. Whether designing a skyscraper, manufacturing an aircraft, or producing medical implants, metallurgical knowledge ensures materials are safe, strong, and fit for purpose.